Welcome to step 4 of the SDL for Kids tutorial series. In step 4, we have the fast track edition, where we do the 3 steps of an SDL all together in one notebook. So that means we will do synthesis, characterization, and planning all in one step. So let's jump right into it. So the requirements for this is a Jupyter notebook, which you will probably already have in front of you, then a BBC microbit, which is this device here, which is a small microcontroller that we can program via USB, and then a Envirobit here, which is this device here, which has a color sensor, which we will use to sense colors. So let's get right into it. In the introduction, we're going to discuss first of all our goal, which is that we want to find the right color to match a target color. So specifically, our computer will not know what the target color is and will have to guess or strategically find the best way to find the right combination to generate on the screen for a target color. So in step 1, we're going to first talk about synthesis. So computers use something called the RGB code. So in RGB code, you have the red color, the green color, and the blue color. And all of those range between 0 and 255. So for example here, if I just run this first cell and define red to 255 and green and blue to 0, then I can create this window here, which is a complete red window. So we are using this CV2 package to create a window, and when we are filling in the RGB code. Now I can, for example, add a whole bunch of blue to the color, and then I will just run this here again, and now you see a pink window. So just make sure that when you run the windows, they will appear behind the browser window, so you just got to make sure you have some space to actually see the window. So now we have a way to generate windows and fill them with colors. So that's already our material that we are filling into the screen. Coming to step 2, we're going to look at characterization. So we want to measure these colors with our BBC microbit. And so first we will have to connect to it, program it, and then request colors from it. So here are the steps. First, we need to program it. So we'll take requests for RGB colors, and then we need to actually send those requests. So we will use the makecode environment, and before you use that makecode environment, we have to first actually get the microbit connected to the computer. So you have the microbit here, and you have the name of the writing, and you have the Envirobit here. And so both of those need to be on the same side. So you can just slot it in like this. And now you got the microbit connected to the Envirobit, and on the other side, you got the color sensor. Then you take a USB cable and you just connect it with the microbit here. And then you see turn it on, show red color. Once you got that connected, you can just hang it over the screen and have the color sensor point at the screen. And now we can open up makecode to program it. So I will use Google Chrome to do that, as it's an easier way to program it. And so I will just go to the makecode environment, and now I will create a new project. I'm going to call it SDL for Kids. Here we go. Okay, so here we will need to first load the extension for Envirobit. So I click on the extension, and then I search for Envirobit, and there we go. If you just click on that, it will be loaded and is available then. And because this is the fast track tutorial, we're going to just copy the code straight away here. In the detailed tutorial, I'll lead you through how to drag and drop the whole program. And for today, we will just copy this JavaScript code. We will go into the JavaScript section up here and just copy and paste. So this JavaScript code will send the red color, the green color, and the blue color once we receive a comma on the microbit. Then all you have to do is just connect to the microbit. So click on connect on the bottom left, press on the pair button, select the microbit, click on connect, and now we're connected with the microbit. Now it's ready to be programmed, so you just press on download in the bottom left. It will download that program onto the microbit, and now we're going to make sure that we are disconnected from the microbit so that there's no interference on the USB cable. I'm just going to close Chrome now, and we're going to get back to the tutorial. If you want to use a different kind of programming strategy, you can follow the link here, where they will explain you how to download the program first onto your computer and then move it onto the microbit. Excellent. So now we can use the serial package to connect to the microbit. And here I will use a Unix command called list all devices to list the name of my microbit. So in this case here, I've got a whole bunch of Bluetooth headsets also connected to my laptop. And this is actually the name of the microbit. So it will be something like USB modem and then followed by my number. So I'm just going to copy this here into the name section. And then I will run the cell. And so now we've got a serial connection ready to use. Then here in the next cell, I will define a function called characterize, and this function, whenever we call it, will send that comma to the microbit. It will receive the data from the microbit, and then it will process it and validate and make sure that we can use it for our experimentation. So let's load that function here. And now as we go ahead, we always want to make sure that we are pointing the microbit onto the screen. So when the window appears, just make sure that the sensor function, sensor element, which is behind here in the environment, is pointing towards the screen. For now, we're just going to run 10 times the characterize function. And it will fail in the beginning as the USB line is still filled with some data, but then it will give us 10 valid measurements here. So I'm going to run it again. This time I'm going to move the microbit a little bit around so you can see that we're getting different color measurements. And now we can be safe that this is working. And again, you can move to the more detailed explanation with this notebook here. Just follow the link. Excellent. So now we've got a synthesis of a color on the screen. We've got a characterization of the color. And now we get to step 3, which is the planning stage. So again, the computer does not know what the goal color is, but we know it's the red color. And we also give the computer the ability to calculate how much a given color is close to that target color. And so the computer can now use different strategies to figure out what the best color is, or the closest color is to the target color, which will be red. So the first one is random, the second one is called grid, and then the final one is called Bayesian optimization, which is using a statistical model to get us as close as possible to the target color. In the random strategy, we're basically throwing dice. So with every color, RGB, we basically have 256 sides on a die. So you throw it and then you just write down the number. And so we define a function called generate random. That is basically throwing 3 dice for us, giving us the numbers, and that's our random RGB combination. And then we're going to calculate the error for that. So that's a function called calculate error. That will take the difference between the target color and our goal color. Okay, so we can just run this here. Just make sure you're pointing the microbit at the screen. And now we've got 10 random colors and the error measurements with that as well. So here we're keeping a list called error values that is filled in with the arrows. So here we calculate the error and then we add it or append it to the list. And now we have that list, we can just plot it here. So you see that there was a color that was closer than a few other colors which were further away. And then here we can process that list even a bit more nicely, and with orange color show the best one so far. And we see here that on step 4, that random color on step 4 was actually closest to our goal color. Now that's not particularly efficient because every time we ask for a random color, we're completely disregarding what we have learned about other colors, and we might even end up running the same experiment twice. So with the grid approach, we are pre-calculating a list of experiments. And so we're going to do the same for the RGB colors. So our colors go from 0 to 255. In our case, we're going to split it by 3. So we're going to have 0, 127.5, and 255. And if we do those combinations for all of red, green, and blue, we will get 27 different combinations. And that will be our grid. So we create this grid, we will loop over this grid. So for each grid combination in grid combinations, which there are 27, we will run them on the screen, and I can run the cell. And again, you see some of those grid combinations are better and some of those are worse. And just make sure you're holding the RGB sensor onto the screen so we get some good measurements. Excellent. So that was 27 experiments. Once again, we are saving them in the error values list, and then we can just plot them here. So as you can see, there's a pattern to this, and this is quite natural because the grid that we created does have a grid pattern. So the experiments you will be running will have a quite structured response. Now, unfortunately, with a grid approach, of course, if my pizza runs at 5 minutes in the oven at 10, we will never know what happens at 7 or 8 or at 9.5. And it might be that the best time in the oven is 9.5 minutes and not 10 minutes. And so that means we would be inefficient with a grid approach. And that is where we get to Bayesian optimization. Bayesian optimization is a statistically maximally efficient way to scheduling experiments. The way it works is taking historical data and building a model, which we then can ask the question, what is the best or most informative experiment to run next? So we can give that a try here. We will load the library, and then we will define a function called calculate candidates, or calculate candidate, that will take historical samples, build a model, and then give us a candidate to run and to evaluate. So here in our experimentation loop again, we have the candidates calculated in this section here, and then this candidate will be run through and evaluated, and then over time the Bayesian optimization algorithm will find the ideal color. So I'm going to give this a run here. I'm holding the sensor against the screen, and we see how the statistical model is making them decisions. They're not random, they're not structured like with a grid, but they're efficient and they're converging to an optimal color here. So we see already that it's found that red tones are closest to our goal color, and it's now just refining which exact red tone will be giving us the exact target color. The computer doesn't know the target color, which we show here with the rectangle on the left. But because it can take the arrow function and learn which RGB mixes are the best, it can actually figure out the target color in quite a few iterations. So again, we do save the arrow values, so we can plot them here, and we see how there's a steady decrease of the arrow, so that we eventually get to the best color, which is the target color. Here's an even more nice plot. In this one, we also plot the RGB values, so we have a second y-axis here from 0 to 255. And we see how in the initial iterations, the Bayesian optimization algorithm is not sure whether green or blue are part of it, and in fact at some point it's choosing quite a bit of green as well. But then soon it realizes that the red part is the one where if it gives more, it will reduce the arrow, and then as it decreases the green and the blue part, the arrow goes down as well. So it would decide to continue to increase the red part and decrease the blue part, and that way minimize the arrow and eventually figure out the true target color. Okay, so congratulations, that is the whole SDL for Kids tutorial in the fast track version. We looked at step 1, which is synthesis, so we're generating a material, a color on the screen. Then step 2, characterization with a real hardware sensor, the BBC microbit. And then step 3, which is planning, we looked at random, grid, and Bayesian optimization, and we got those working and found the right target color in just less than 50 steps. So this completes the tutorial series, and now you can look at the next tutorials or the exercise notebooks, and there you can answer some questions and do some programming yourself using the microbit, using the random strategies, using Bayesian optimization, and get your own feeling for how an SDL works and what you can do with it for yourself. Thank you very much.